Welcome to the presentation of the multi-partner project Application-Specific AI Processor for Intelligent Sensor Signal Processing and Autonomous Driving. My name is Sven Gesper and I will give you the details about the system in this project. This is a multi-partner project with work from partners of industry and university. So our consortium consists on the industry side of Dream Chip, Bosch, Cadence and the associative partner IBEO. On the university side, the partners are the RWTH Aachen, University of Hannover, TU Kaiserslautern and the TU Braunschweig. The goals of the ZuSE project is to develop a processor architecture and to evaluate this platform in an embedded use case. So the developed scalable processing platform allows the massive parallel computing and implements a vertical vector processor. For evaluation, 3 use cases from sensor signal processing and autonomous driving were chosen and implemented and gets further evaluated. The work packages of the projects are shown here. So the project is coordinated by the University of Hannover, and from the algorithmic perspective, the companies Bosch, Dream Chip and the University of Hannover are implementing different applications. The hardware implementation is done by the TU Braunschweig, together with the TU Kaiserslautern, who implements the memory controller for the platform. Based on a FPGA prototype, a first platform will be used for application development. At the end of the project, the processor will be published open source. The ASIC design offers further evaluation when the final prototype is taped out. To include an ecosystem for simulation, Cadence develops a virtual prototype. The compiler support for the system comes from the RWTH Aachen. Regarding security aspects, several concepts to improve the security of the platform and the system design are evaluated. The current state of the project offers an FPGA prototype, which is currently used to optimize the implementations of applications. Based on this demonstrator, first evaluation results are available, which focus on the execution characteristics of an exemplary CNN application. The further work includes the final ASIC design, tape out and the evaluation of this chip prototype. The specified applications of the system are based on camera data inputs, radar signals and a LiDAR sensor. For the camera-based application, a side mirror camera is used to identify the 4 classes: pedestrians, bicycles, vehicles and motorcycles. These camera signals are used as input for a convolutional neural network that extracts and tracks 3D bounding boxes. The result of this application can be visualized as shown in this example. The second use case is radar sensor signal processing. It is also used to classify objects in advanced driving assistance systems. The radar signals require several processing steps like shown here. And one example is this 2D fast Fourier transformation, which are required before a final neural network classifies object. Due to the robustness of the radar sensor signals, this application also fits well into the autonomous driving use case. The LiDAR sensor of this project is another application which processes a point cloud. The result is an image which is segmentation, which is shown here in this example. The processing steps of this application transform the 3-dimensional point cloud into a 2-dimensional plane before running a neural network-based segmentation. In this project, a hardware architecture was developed which implements several components. As shown here in the middle, the application of the processor runs on a RISC-V based processor. For compute-intensive tasks, the configurable vector processor array is used, which is shown here. The DMA units transfer data from the external memory via a data cache. The external memory is controlled by a memory controller which is optimized to improve the performance. Furthermore, the system allows the communication via this Axibus, and it has dedicated control and status registers for external synchronization. As mentioned, the vector processor is an array made of a configurable number of processing units and lanes. So there are several clusters, each of them contains vector units and a DMA. The DMA transfers data from external into the local memories of the vector units. These shared memories are accessed by a dedicated LOT store lane, and the processing vector lanes process the data in vertical vector instructions. So these ALU inside the processing lanes process a single register file element in one cycle. To achieve a data parallel execution, the instructions are broadcasted to multiple clusters, vector units, and processing lanes. The implemented vertical vector processor concept is shown here. So on the right side, you can see the vertical concept allows a flexible vector length in opposite to the horizontal vector process. Due to this flexible vector length, the number of subwords is not limited. Furthermore, no complex subword permutation instructions are needed, as the addressing scheme uses flexible vector element addressing. The element addressing is shown here. So the addressing mode for this vertical vector processor allows individual address for each operand. So each operand describes the vector with the three-dimensional address coming from alpha, beta, and gamma encoded in the instruction. And the vector length is defined by x-end, y-end, and z-end. Corresponding to the selected parameters, one operand can select elements in a linear addressing, a 3D strided addressing, or different modes. The data exchange between vector lanes can be done via the external shared memory or by a chaining mechanism. This is shown here, like when you have two neighbor vector lanes, you can exchange data to process them in the neighbor lane. Furthermore, this mechanism is extended to modify the address in a neighbor lane. This allows indirect addressing. As the address is calculated for each operand, the vector lane requires 3 hardware addressing units. By the register file size, which is limited, the calculation complexity for this address calculation is limited as well. The processing in the configurable array includes a configurable number of DMAs to transfer data from or to the vector processor's local memories. As each cluster contains a DMA, several parallel working DMAs transfer data. With this DCMA, which is a data cache, the parallel transfers are merged to a single port access to the external memory controller. The cache also enables the reuse of locally stored data and reduces redundant data transfers. For a high data throughput to the external memory, an optimized DDR4 memory controller is developed in the project. The optimizations include a smart refresh management to reduce latencies and to optimize energy requirements of memory transfers. The controller includes extensions to improve security aspects. For these aspects, it implements AES 128 data encryption and decryption unit, which with a local one-time generated key. The programming interface to the vector processor uses C code to compile a RISC-V binary which is executed on the processor. The code defines vector instructions in libraries, and in this example you can see a 9x9 convolution within a single vector instructions. So 81 vector elements are multiplied and accumulated. And the parallelism is done by broadcasting these instructions to multiple vector units which process different loaded data from the local memories. For a fast execution, the developed compile flow optimizes the compilation by a custom compiler and adapts to the implemented RISC-V architecture with the vector processor interfaces. As many implementations for the applications use convolutional neural networks, a library was developed to map high-level network structures efficiently to parallel vector instructions. The tool flow implements the quantization of the network and the generation of vector processor instructions. The processing of different data segments is then executed on the RISC-V processor. For debugging and evaluation, a virtual prototype system was developed. This includes a complete platform and can be used to detect software issues by non-intrusive evaluation techniques. This is the result of the vector processor architecture which was implemented and optimized for Xilinx UltraScale FPGA board. The evaluation results show the characteristics for an exemplary small CNN. The convolutional neural network utilizes the maximal available resources on the vector processor. The configuration of the vector processor array on the FPGA contains 8 clusters with 8 units each and each unit with 2 processing lanes. This results in 128 parallel vector lanes, occupying up to 85% of the configurable logic blocks on the FPGA. The maximum operation frequency is 400 MHz. So with this, the theoretical peak performance of this vector processor architecture reaches 59.2 gigamax or 102.4 giga operations per second. With the achieved frames per second of this CNN structure, which is about 126.9 frames per second, the efficiency of calculations achieved about 60%. In comparison to a GPU execution with 512 CUDA cores, the efficiency is much higher as the use of DMA transfer data efficiently, and the vector instructions enable efficient instruction encoding. In summary, the developed platform of this project is a configurable vertical vector processor array whose goal is to achieve high performance and high utilization efficiency. The FPGA prototype shows high effort on base of a small evaluation CNN. Based on 3 use case applications for advanced driving assistance system, the system will be further evaluated. Ongoing tasks are the tape out of the ASIC design and publishing of the open source system. Thank you for your attention. Hello, I will show now a demonstration of the vector processor system on an FPGA which is processing live pictures with a small CNN. So our system is running here on this FPGA board. On this board there is a Xilinx ZuSE-KI FPGA, which includes a dedicated ARM processor which runs Linux to manage the FPGA part. On the FPGA there is a vector processor configuration which has 8 clusters and 8 units. It runs at 400 MHz and it processes the application. So the data which is processed comes directly from this USB attached webcam, which we will use to generate new input data. This small CNN which is running on the vector processor processes these data, and the Linux on the ARM processor visualizes it. This is done by this network attachment, and I'm using my laptop to visualize the data. So I can take the webcam here with me. I will place it on this table, and I will also start OBS Studio to record the webcam picture. So now you should see me in front of this webcam. So let's check if this small CNN is capable of recognizing some pictures. So I have printed a horse, and when I place this horse in front of the webcam, well, it recognizes the horse mostly, but it's not a really accurate CNN, so you can see there's sometimes a dog or something else. But usually a person like me, when I sit down here, it's recognized pretty well. So, this is a demonstration. We were using the FPGA, which is placed on the effector processor, which is placed on the FPGA. The system is connected to my computer to visualize the results of the CNN processing. In totally, the achieved frame rate is about like 126 frames per second due to the processing speed of the vector processor system. Thank you for your attention.